guys, so this is some supplemental notes for chapter 5. I made a little thing of stuff I want to cover with you guys. So I'm going to cover forming bonds really quick. And I know we've touched upon this, but I feel like we need to go into more detail. So we have ionic bonds, right? And so some of the things to note with ionic bonds and that they are the transfer of electrons. So they transfer electrons from one atom to another. Let's go ahead and make an example. So here is my nucleus. I have my example set up here. Let's see. So if I had lithium, which is going to have 3 protons and 4 neutrons. Okay. So remember I said 3 protons, so that's going to be 1, 2, and lastly 3. Now if you guys recall, lithium is found in group 1 of the periodic table, so this is lithium. So therefore it has 1 outer electron, so 1 valence shell available for bonding. Lithium, and we're going to combine it with fluorine. Okay, so fluorine is 1, 2, 3, 4, 5, 9. Okay, so let's go ahead and do 9 protons. 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's give it some neutrons. Okay. Alright, so here is my fluorine. That's its nucleus, and we're going to have the first shell, which is going to have 2 electrons. And the second energy shell right here, which is going to have the rest of my electrons. So 9 take away 2 is 7 more. So I'm going to have 1, 2, 3, 4, 5, 6, 7. Okay. All right, so what's going to happen here is that our metals transfer the electrons to the non-metals, okay? And they're going to then combine together after that is done through electrostatic force. So let's show this. This electron here is going to leave fluorine and leave lithium and attach to fluorine. Why? Well, if you guys notice, fluorine has a lot of protons in this center, a lot of protons. That means the effective nuclear charge inside of fluorine is really, really high. So its ability to attract electrons is also higher. Why? Because it's more positive inside. So it's spewing with positivity. And remember, like attracts, or oh god, I'm going to say that wrong. Opposite charges attract each other. So the lithium, when it gives away its electron, it becomes lithium with a +1. And fluorine, when it gains an electron, becomes fluorine with a -1. So now this creates an electrostatic force of attraction. So the electron, so after electron transfers, the atoms attract through electrostatic force of attraction. Basically means opposite charges attract. Okay, so the opposite charges are attracting. All right, so the opposite charges attract. Once that happens, you're going to get atoms that look like this. So you're going to have 1, 2, 3 here. So drawing our lithium, okay. All right, and then here is going to be our fluorine. And I'm just going to exaggerate how much bigger that is. And okay. Just adding all my stuff in there. Okay, I didn't count the neutrons, but either way, now these are being attracted by electrostatic force. You notice that it's not really touching itself. Okay, they're not touching, but they are attracted together. So somewhere in the between, right here, it's like magnetism almost. Okay, they're attracted to each other. Right. All right, so this right here, lithium was a metal and it lost an electron, right? And once it loses an electron, we remember it's called a cation. And then fluorine, when it gains an electron, so this is fluorine with its gained electron, it's known as an anion, right? So this is gained electron. So now it has a negative charge. And a cation loses electron, and therefore it gets a positive charge. Okay, so a couple things is that metals and nonmetals, their net charge is going to equal to 0. So when you combine these atoms together, you're going to get a net charge of 0. So continuing with our example, we had lithium, and then lithium plus fluorine, and they combine together to give us lithium fluoride. And how do we know it's a 1:1 ratio? Well, lithium can make a +1 charge because it's in group 1, and fluorine can make a -1 charge. It's in group 17, right? So therefore, a +1 plus a -1 is equal to 0. So +1 plus a -1 is equal to 0, right? So they're not going to be making any more, yeah, sorry. So it's now good. It's good, it's good. All right, let's go ahead and move on. All right, so covalent bond. All right, so a covalent bond is different from a ionic bond in the fact that it doesn't transfer electrons. Electrons are shared. Okay, so electrons are shared in a covalent bond. Okay. And they form molecules. Right? So they form molecules. All right. A couple things is that covalent bonds are made only by non-metals plus non-metals. And if we forgot to write it on the other one was metal plus non-metal, which I think we noticed with the lithium fluoride example. Right? Covalent bonds also have low melting points and low boiling points. Okay. So an example of a covalent bond is sugar. If you put sugar in the microwave, you're going to catch it on fire. If you put salt, which is an ionic bond, in the microwave, it's going to take a very, very long process and super high heat in order to melt the salt. Okay, so covalent bonds, low melting, low boiling. Ionic bonds have a higher melting and higher boiling point. Covalent bonds can also have partially charged poles, and they do not conduct electricity. Okay. So they can have partially charged poles. Basically, all that means is that one part of the element has a charge and the other side of the element has another charge, but they're partially and most of the time temporarily lit. They do not conduct electricity. They do not conduct electricity. All right, so let's go ahead and show an example of our covalent bonding here. Let's use, let's grab a periodic table real quick. Kind of tired, so the elements aren't popping in my head right now like they should be. All right, let's covalently bond oxygen and oxygen together. Why not? Okay, so oxygen has number 8 and it has 6 valence electrons. Okay, so it has 8 protons. So inside of my nucleus, I'm gonna do 8 protons. 1, 2, 3, 4, 5, 6, 7, 8, and then 8 neutrons. 3, 4, 6, 7, 8. I'm gonna go ahead and draw my first shell. And the first shell is always really close to the nucleus, right? Because that nucleus is pulling it towards it. All right, so this shell very close to the nucleus, because the nucleus is, the positivity of the nucleus is pulling the electrons towards it, right? It has a high effective nuclear charge. Now, first energy level, it doesn't have any shielding effect, 0 shielding effect, right? Once you get to the second energy level, you're going to start experiencing shielding effect, which basically means that these 2 electrons are shielding the electrons in the outermost shell from the nucleus. Obviously, it's only 2 electrons. They're not going to do much for shielding. All right, so I said 8 electrons total. I've used up 2. I got 6 to go. 1, 2, 3, 4, 5, and 6. Okay, we're going to have 2 of these because I said oxygen and oxygen. Okay. All right. So now we have our oxygens. They're together, okay. And what's going to happen is that they're going to share, right? And they're going to share their orbital together. And what that means is that these will share an orbital, and then these will come together, and they will also share an orbital here. So they're going to move out of that location and move to the center location. And you're going to end up with, okay, let's see if I can draw a little bit faster. you're going to end up with this diatomic element of oxygen, in which it's going to have two pairs of bonding electrons in the center of it. So they're going to bond together, right? And this bonding is called the sharing of electrons. So they're going to share orbitals, right? And that allows them to complete their octet. Now you notice that I said this is a pair, a double pair. Okay, so we have different types, 3 different types of bond pairing. You have one pair of electron being shared, so one pair, okay, that is equal to a single bond. So it's one pair of electrons, so that's 2 electrons together. Then you're going to have 2 pairs, which is going to be called a double bond. And that's what you see here. It's 2 pairs, and that's a double bond. So your electrons, you're going to have double bond. And you could have 3 pairs, and that's called a triple bond. Okay. All right, now a couple of things about these bonds, and I actually should have drawn these to better represent that, so I'll use a marker to do that, is a single bond is a very large bond, okay? So it's a large bond, and it's the weakest bond of them all. A double bond is shorter than a single bond, okay? And it's going to be much stronger. And a triple bond is the shortest of all bonds, and it is also the strongest, okay? So they increase in strength. Let me move this side. So they're going to increase in strength, okay? So as you go down, the bonds get stronger, right? They're tighter together. So it increases in strength and they tighten up, so they get closer together and closer bonds. And the closer the bonds are, the harder it's going to be to tear those 2 atoms apart from each other. Okay. All right, let's go into polar, nonpolar. Okay. So polar molecules are asymmetrical molecules. And an example of what we mean by that is quite simple. You have 2 atoms, and they're going to be sharing electrons, but you're going to see it like this. You're going to see that the electron spends more time around another atom than it does with both, okay? So their dipole moments are going to be different. Since the electron's going to spend more time on this side, that means that this dipole is negative and that this one is going to be a positive dipole. We can clearly see that there is a polarity issue here. So this right here is called a polar molecule. It is asymmetrical, right? And then you could have your nonpolar molecule. And these are more symmetrical. So I'm not going to write symmetrical. They're just more symmetrical, okay? Actually, I'll write symmetrical, of course. They're close enough to being symmetrical, but not all the times are they going to be considered symmetrical molecules. So if we put them down, you should get about equal quantities on both. So that way you can constitute polar and nonpolar. Now, if we base it off electronegativity, okay, in order for it to be nonpolar, it has to fall between 0.0 to 0.3. That's for your electronegativity. In order to be polar, you have to fall from 0.3 to 1.7 or higher. And if your electronegativity value is in this, then you're going to be highly electronegative. Alright. That covers that part, which is forming bonds and electronegativity. Let's go into this shielding effect right quick. Okay, so shielding effect, there's not a lot to it. It basically means that the valence electrons are being shielded by the inner electrons from the nucleus. Okay, remember the nucleus has gained a lot of protons, and as it gains those protons, it is attracting more and more to it, and it's causing different things. So the shielding effect basically is those inner electrons protect the outer electrons from the nucleus. Things that increase shielding effect is an increase in atomic radius. The bigger your atom is, the more shielding effect you're going to have. All right. So quick example. Okay. All right. So this is going to be our energy levels. I only drew some of them. So this is 1, 2, 3, and 4. You guys notice that the separations between them has increased. Okay, and that's because the effective nuclear charge isn't as strong anymore as you add those layers to it. All right, you guys, that's it for this part, and then I'm going to cover formal charge in a different PowerPoint. Ciao.